Hi everyone, it's Martin Shkreli, and I'm here to do chapter 11 of the chemistry work. Chapter is called Properties of Solutions, and so it's going to be a little bit dry, very stoichiometric, not very useful theoretically. We're going to pick up a couple of interesting and cool things, but nothing totally important. So if you don't have the time and you just want to study pharmaceuticals, this is probably a chapter you can skip safely. Having said that, I don't recommend that you do that if you are interested in a full knowledge of chemistry, because that's going to be pretty important. Well, let's get into it. Let's talk about solutions. So we know what a solution is. It's a homogeneous mixture, right? But we like to talk about solution compositions and solution concentrations a lot, so let's do that. For example, I'm drinking a coffee, which isn't quite a solution. But the water, I guess you could call it a solution. And I like my coffee very sweet, so there's only a few ways in science at least, to discuss the concentration of sugar in a solution. Nice and sweet. So it's a more concentrated solution. So there's a lot of ways to talk about concentration. And this isn't mental concentration that you need for, let's say, a chess game, which I don't have. This is more about the amount of solute in the solvent, right? So in this case, the solute is sugar and the solvent is water. Sugar, or sucrose, I guess, is a better way to put it. So anyway, we learned about molarity in chapter 4, just to review. Molarity is a really good way to explain concentration. And it's just moles of solute divided by liters of solution. We learned that a few times, right? So let's learn another way, mass percent. Mass percent. This is the mass of the solute divided by the mass of the solution. This makes a lot of sense to me, right? If you have something that's 10%, you have to express it as a percentage, so you multiply it by 100%. So if you have something that's, you have 10 grams of sugar in 50 milliliters of water, that's what, 1 over 5, a 20% sugar solution, right? So that makes sense. That's another way to do it. A third way to do it is we'll call the mole fraction, which is similar to the mass percent, except it's the moles. So say solute over solute plus solution is the mole fraction, and that makes a ton of sense. And finally, we have this new one that I encourage you to learn called molality. Not molarity or morality. Morality is totally different. But molality, which is moles of solute, similar to molarity. The numerator is moles of solute. The denominator is different. It's actually kilograms of solvent. So this is easier. If you want to do it with a weight-based denominator, you get molality. If you want to do it with a volume-based denominator, you get molarity, and you can obviously convert between the two pretty easily. So the book wants us to do an ethanol solution. This is a alcohol that we drink. Some of us drink, at least. I hope you don't drink too much. 1 gram of ethanol. So we'll just put down the ethanol, C2H5OH. We're going to learn a lot of these organic hydrocarbons in chemistry over time, but C2H5OH with 100 grams of water. So they're going to put, and this is important because this might trick you. They put 1 gram of ethanol in the 100 grams of water, and they give a final volume of 101 milliliters. So they remember the new volume of the solution is 101 milliliters. It is not 100. Remember, 1 gram equals 1 milliliter. Never forget that. All right, so molarity we can calculate pretty easily, right? How many moles do we have here? Well, we have 2 carbons, so that's what? Carbon 12, right? C times 12 times 2 is 24. Hydrogen, we've got 6 hydrogens. They weigh 1 each, so that's 6. Now oxygen weighs 16, and we have 1 of those. So this is equal to 46. Is that about right? Yeah, 46.07 if you add all of the decimals. So that's grams per mole of ethanol, 46. Anytime you drink a beer, you can say, well, the ethanol in this beer is 46.07 grams per mole. And whoever your bartender is will stop serving you, I would imagine. So in any event, we have 1 gram of ethanol, which means we have a lot less than a mole. In fact, we have precisely 1/46 of a mole. And then if we multiply that, well, we can actually just calculate it. 1/46 of something is 2.717 times 10 to the negative second, or 2.0217, right? So 12 means 2.17 times 10 to the negative second. So this is how many moles we've got. And we know molarity, it's what? Moles over liters. So we got to convert 101 milliliters to liters, so that's simple. That's just 0.101 liters, right? 0.101 liters. And we can actually do this math very easily, right? This divided by this is equal to 0.215 molarity, or 0.125 molar. Okay, so that's easy. How about, we did this in chapter 4, in case you don't remember. So how about mass percent? Well, this is simple. We got 1 gram of the solute, which is the ethanol. And then again, very, very tricky here, we have 101 grams of the total solution, right? This is the 1 gram of the ethanol plus the 100 grams of the water. And we do the math, and it's not 1%, it's almost 1%, it's 0.99, a little less than 1% ethanol. That would not get you very, very drunk very quickly, 1%. I think things like whiskey and things like that are like 20%. I know maybe beers are like 6%, so this is a very dilute solution of alcohol. And I'm a lightweight. How about mole fraction? How about mole fraction? Well, let's see. We've got 2.17, right, times 10 to the negative second moles of ethanol. We calculated that. How about water? Well, 101, well, so it was 100 grams of water, if I recall. And water weighs 18 grams per mole. So if we have 100 grams of water, we have more than 1 mole. In fact, we have 100 divided by 18, which is 5.58. So if we divide, we have a very small amount, less than like 2% of 1 mole, 0.02 moles of ethanol, but we have 5.5 moles of water. So the mole fraction is 0.0389. 0.0389, the mole fraction. And finally, we have molality. Molality is easy because it's just moles. Instead of liters and molarity, we have kilograms. And we know that this is 0.1 kilograms because it was 100 grams, right? So 0.1 kilograms. And notice in molality, just like in molarity, we don't adjust the solution, it's just the solvent. So instead of 101 grams, it is actually 100 grams of H2O, which is 0.1 kilograms. So if we add this up, we get 0.217 little m, which is molality. And notice the molarity is big M, and that's 0.215 molarity. Finally, I want to introduce you to this concept of normality. Normality. This is kind of a tricky concept. This is on page 513. And the concept of normality, let's just take a look. Let's take a look at hydrochloric acid. The molar mass is 36.5 grams per mole. The equivalent mass is 36.5 grams, 36.5. So what does that mean? What does that mean? Well, it means that in normality, what we're focused on is for acids and bases, is how many protons can it donate. And so 1 molar here is 1 normality here. And so if we look at or sulfuric acid, let's call it sulfuric acid, this is interesting because it's donating 2 protons. So the equivalent mass is actually 49. So 1 molar is actually 2 normal. And so the point here is that we're worried about how many how many sort of moles of electrons and things like that can we give out. And so we either divide by 2 or whatever the functional unit is. And it doesn't have to be acids and bases. Here's just a normal CaOH2, calcium hydroxide. I guess this is a base. And it's going to give 2 OH units, right, per molecule. So the normality is 2. And so anyway, we'll need this from time to time when we do various calculations. All right, let's get into a different topic. Oh, I have a bit of a cold today, so. All right, let's see. 11.2. This is page 514. More than halfway done with the book, which is great. Making good progress. This section is called The Energies of Solution Formation. And the good thing about this is we're piecing together things that we've learned in prior chapters. So the biggest thing we want to learn here is like dissolves like. And this is sort of the opposite of opposites attract. Here, you have for dissolving, for solubility, you have the concept that like dissolves like. So a polar solute can be dissolved in what? In a polar solution. And it can't be dissolved in a nonpolar solution. And likewise, nonpolar will dissolve in nonpolar. So that's how solubility works. We're going to understand a little bit more about solubility, but there's sort of 3 steps. 3 steps to form a liquid solution. The first is we want to expand the solute. And what that means is we're going to break the intermolecular, intermolecular forces so that we have individual solute components, right? Like Na and Cl, you want to break those apart. Next, the intermolecular forces, so expanding the solvent, same concept. And then finally, allowing the 2 to react. And this sort of makes intuitive sense. Solution and the solvent to interact. That makes a lot of sense. And all 3 have some kind of energy requirement, whether it's giving or taking. So the delta H, or the enthalpy heat of the solution, is equal to each of the 3 steps. And we'll talk about these 3 steps in some detail. And so obviously if energy is absorbed, it'll be a positive. If energy is given off and released, it'll be a negative. So what we'll often see is that delta H3, when they interact, that'll be an energy releasing phenomenon. And these 2 should be energy requiring phenomenon. So think about that for a second. So let's look at an example. Let's take sodium chloride. And we'll say that to separate these out into ions, requires some energy, right? Requires 786 kilojoules per mole. And we'll call that step delta H1. Delta H1 is 786 kilojoules a mole. All right, let's look at the next step. We'll take water, and then we'll take these ions and as gases, right? And then they'll become aqueous. And this entire process releases 783 kilojoules per mole. So the net amount is 3 kilojoules per mole. That's the enthalpy heat of solution here, 3 kilojoules per mole. So we add all of these up. And this is both delta H2 and delta H3 in one step here. The second part here. And so this is the enthalpy heat of hydration. That's what we call this delta H plus delta H2 plus delta H3. And so the point is this requires some energy. And that's why when we put salt in water, we need a little bit of energy. We need a little bit of energy to make it dissolve. And so there's a number of other concepts here. Like a good example is any process that requires a large amount of energy, like oil in water would require a large amount of energy. These things won't happen because they require too much energy. That would require 1,000 kilojoules per mole, and that just won't happen by accident. So that's an important sort of concept to think through. All right, let's keep playing with this idea of solubility. I'm on page 517 and 18. Factors affecting solubility. And this is going to be really important. We're going to learn a lot about drugs right now, a lot about pharmaceuticals. So this might be interesting to you. So maybe when I said you can skip this, I was wrong. We'll learn the concept of hydrophobic, which means water-fearing. And this is going to be an extremely important term for you to fully understand as you get into pharmaceuticals. Water-fearing. And lipophilic means fat-loving. And generally anything that's water-fearing will be fat-loving. And then we have the opposite. We have hydrophilic and lipophobic. You don't hear the term lipophobic a lot. The preferred term is kind of hydrophilic. These are both kind of preferred terms, lipophilic, and I think is a little more preferred than hydrophobic. So we tend to go with the philic than the phobic. So anyway, this is water-loving, and this is fat-fearing. My girlfriend tends to be lipophobic. And so anyway, the point here is that something that is water-fearing or fat-loving is non-polar. And something that is water-loving is polar. These are really important. Let me draw you an example. This is let's see, vitamin C. So can you tell if this is, which one of the two this is? Well, I'm not drawing the carbons because that's what we do in organic chemistry. I'm sort of preparing you for that. The book draws out all the carbons. But in this case, this is pretty obvious that this is a polar molecule. Why? Well, you have all of these electronegative groups. You have all of these electronegative groups. 2, 3, 4, 5. These are all going to have polarities. They're going to have dipoles that have the oxygen is going to pull the electrons towards it. This is vitamin C. This is very polar. Let's try a different one. This is a very well-known molecule. Extremely important in medicine, in fact. See if you can guess it just from looking at it. Some people can. is a very well-known structure. It's called vitamin A. And it's the basis for retinoids. So a good example of retinoid is Accutane. Vitamin A. And this is extremely lipophilic. Extremely lipophilic. You have only basically these fatty carbon chains which are nonpolar. The only polar part here is this OH at the end, but that's not enough. That's not enough to overcome how nonpolar it is. And so this ends up being extremely important in medicine. You know, this whole concept is extremely important because when we design drugs, we need to make sure we have the right polarity. And generally, we kind of want to avoid too much polarity. Let me give you an example. Let's look at atorvastatin, one of the most famous drugs of all time. It's called Lipitor. You can see that it's generally nonpolar. It's got these polar parts here, for sure. But that's important for it to function with the enzyme. So some of it's polar, some of it isn't. You need just enough polarity to be soluble, hopefully, and not enough that you're too polar, because you can't cross a lipid bilayer. The thing about cells is a cell is surrounded by lipids. It's called a lipid bilayer. You have these lipid bilayer, and the size of accommodation is only so much, but these are non-polar. So if you try to stick a polar molecule in here, it might not be able to go in. And a non-polar molecule can enter the cell a little more easily. Yeah, you can definitely tell polarity by the structure. Let me give you another example. I think of one off the top of my head. I take a drug every day called loratadine. Here it is. It's extremely non-polar. You have a little bit of poles at the end over here, but in general, it's non-polar. So drugs, especially drugs that we want to enter the brain, have to be extremely lipophilic. In fact, there's one way to tell is this log P. So we'll get to this in a future lesson. The partition coefficient log P is a way to tell the lipophilicity of something. We do this little experiment and we can determine it. And the blood-brain barrier, log P, generally has to be a certain amount. Let's take a look. Maybe this will tell us. So you want the log P to be in the 0 to 2 range, or closer to 2 is what they say. 2 or above. So you need it lipophilic. If it's hydrophilic, it won't get into the brain. So look at how concentrated the CNS drugs are, or the brain drugs are, because they're very lipophilic. You can't have a brain drug that's hydrophilic, generally speaking. The molecular weight often has to be below 1,000 molecular weight, because that's the size of the lipid bilayer. So hopefully you learned something about drugs there. Next thing I want to teach you about is solutions and their solubility when it comes to pressure. We're going to learn very easily a simple law called Henry's law. Henry's law. And Henry's law simply states the solubility of a gas, and this only applies to gases, increases directly proportionally with pressure. So concentration increases with pressure. And this, we know this from soda. Carbonated soda has carbon dioxide, and the higher the pressure, the more solubility we get. So the amount of gas dissolved is directly proportional to pressure. We don't have to get into that too much. We can also get into temperature. So we learned a little bit about pressure. And it only really relates to gases, but temperature is a little bit interesting as well. And there's some generalities here. It's very difficult to predict. That's one thing to understand. It's difficult to predict temperature dependence on solubility. In fact, we generally just want to observe it experimentally. Having said that, gas is pretty easy. Gases are pretty easy. The solubility of a gas, in water, and this is important, this only applies to water, you'll see why in a second, decreases with increasing temperature. And page 520 describes this pretty well. Decreases with increasing temperature. The opposite tends to be true in non-water. So go figure. All right, let's move on to 11.4. The vapor pressures of solutions. We're all studying from the same book called the Zumdahl and Zumdahl chemistry book, 9th edition. All right, so vapor pressures of solutions. So as you can imagine, solutions actually have their own vapor pressure. And we're going to learn something called Raoult's law. Raoult's law, which I'll just leave right here. And it's the pressure of a solution is equal to the amount of solvent multiplied by the pressure of the solvent. And we'll talk about what this means in a second. The observed vapor pressure of the solution, the mole fraction of the solvent, and the vapor pressure of the pure solvent. So we're going to talk about what this means in a second. But it's important because when we talk about solutions, we're going to find that a lot of the times when we have a solution, the properties of the solution change quite a bit. So equilibrium is one of the things that we're going to think about. So with respect to Raoult's law, let's do an example. So the expected vapor pressure at 25 degrees Celsius for a solution prepared by dissolving 158 grams of sucrose, which has a molar mass of 342.3 grams per mole, in 643.5 centimeters of water. What is the Raoult's law? Okay, well, how many moles? We need mole fractions, so we need to know how many moles of sucrose we have. Well, we have 158 and the molar weight is 342, so that's something like 0.4616 moles of sugar, of sucrose, table sugar that we've got. Okay, so that's good. So now we need to know how many moles we've got. Well, we know that we have 643 cubic centimeters of water. We know the density of water is close to 1, so if we multiply by the density of water, we get 641 grams of water. We know the molar weight of water is 18, so if we divide by that, we know that we have 18, but how many moles do we have? 35 moles, 35.6 moles of water. So the mole fraction is going to be that divided by that, which is very, very, going to be a very small number, if I would imagine. Let's see. Well, it's actually the mole fraction of water. So mole fraction of water is 35.6 divided by the solution, which is going to be close to 100%, right? It's going to be 98.7% of that solution was water. 98.7% of that solution is water. So we could start to do the vapor pressure of the solution is what we're trying to solve for. So we know the mole fraction of water is 0.987 in this case. And Raoult's law says to solve for the pressure, we're going to multiply that by the pressure in normal circumstances. So normal vapor pressure of water is 23.6 torr, 23.76 torr. So we multiply the two, it's going to be 23.46 torr. So basically the vapor pressure went down because we added sugar to it. And this is really cool. We added 158 grams of sugar into (643.5 cubic centimeters of water. And the pressure, the vapor pressure, went from 23.76 torr to 23.46 torr. So the sugar reduced the vapor pressure. And we're going to see that quite a bit. It's important to know that sugar is a non-volatile solute. Non-volatile. This Raoult's law only applies with a non-volatile solute. There's a lot of adjustments to Raoult's law that we can do, but the basic example is that solutes will change the properties of a solution. And to further that idea, we're going to look at page 527. We're going to look at what we're going to call the boiling point elevation and the freezing point depression. And that's what kind of we just looked at. But these are called colligative properties. Colligative properties. Then the point is that by adding these solutes, we tend to, for example, a non-volatile, like sugar, a non-volatile solute elevates the boiling point of the solvent. That makes sense. That makes sense. The same thing applies to freezing point. It will depress the freezing point. So this all should make a lot of sense to you. And I'm not going to go through the details too much, although I will say that we'll do one example on page 530. On page 530. And so the way that we solve for this is we take something like delta T, or change in temperature, is equal to KFM solute. And we'll call this the molal freezing point depression constant is this. This is a very similar equation to Raoult's law. I'll show you how to use it in a second. I'll show you how to use it. And of course, M is the molality. So we learned molality, and that's why we learned it. Right, so the problem on page 530 is pretty cool. It's a chemist is trying to identify a human hormone by determining its molar mass. He wants to know the molar mass of this mysterious hormone. And this is not uncommon. We want to know the molar mass. We have a sample of this hormone, and it weighs 0.546 grams, and we're going to dissolve it in 15 grams of benzene. 15 grams of benzene. And the freezing point depression was 2.240 degrees Celsius. It decreased the freezing point by 0.240 degrees Celsius. And now we can calculate the molar mass from this. This is pretty cool. It seems like it'd be hard to calculate the molar mass of a mysterious dissolved object, but just by determining how much it changes the freezing point, which we could determine pretty easily, just through experiments, we can determine the molar mass of this compound. So the molality of this mysterious hormone is going to be equal to, because we know that delta T equals Kf times mole of the solute. So if we divide both by Kf, we isolate molality of the solute. So the molality of this hormone is just equals delta T over Kf. We know what delta T is, 0.240 degrees Celsius. And the molality of the solvent is equal to not only the moles, not only the delta T, but now the Kf. Now the Kf of benzene is well known. You can actually look it up. You can actually look it up quite easily. And it's actually 5.12 degrees Celsius per kilogram or per mole. Kilogram per mole. That's the normal Kf. That's the normal Kf for benzene. So if we add this up, we get 4.69 times 10 to the negative second moles per kilogram. That's the molality. That's the molality. And so we know that molality is the moles of the hormone over what? The kilograms of the solution. And how many kilograms do we have here? Well, we've got 15 grams, so that's 0.015 kilograms. And we know that the molality is equal to 4.69 times 10 to the negative second moles of kilograms. So we can determine, if we multiply both sides by, I guess, 0.015, we can determine that the moles of hormone that we've got is 7.014 times 10 to the negative fourth. That's how many moles we've got. Okay, now how do we get the molecular weight? Well, we know that we put how much of this hormone, 0.546 grams, and that got us that many moles, less than 1 mole. So if we do that equality, let's see, 7.014 times 10 to the negative fourth moles, half a gram roughly, is equal to that much. So let's see, x would be equal over 1 mole. So we cross multiply, and we find out that x is 776 grams per mole. So it's a lot of mental and arithmetic gymnastics, but it's amazing that we could find the molecular weight through this simple process. So the delta T equals Kf m solute. You can look up Kf or Kb if you're looking for the boiling point. It's Kb, delta T equals Kb, molality of the solute. And this all sort of comports well with Raoult's law. Okay, so we got one last topic to cover, and it should be pretty simple, and it's called osmotic pressure. And I actually struggled with the way the book presented this. I didn't love it. So I might struggle here a little bit, but I'm gonna do my best. I think the best way to understand it is not the first example they give, but it's actually this example. So this is this weird connected test tube. And here we have something called a semi-permeable membrane. And we hear the word osmosis a lot. We hear the word osmosis a lot. Osmosis. And basically it's the flow of a solvent into a solution. So we'll call this the solution. And this is a pure solvent. Often this will be something like water. A solution could be, I don't know, it's not a good example of a solution, but blood would be a solution. So this pure solvent will flow through the semi-permeable membrane where only solution can go in and solute can't escape through the semi-permeable membrane, for example. It's got small enough that the big portions, the big molecules can't go the other way, but maybe a solution can. And so the pressure required to stop this flow is called the osmotic pressure. And again, if you have some difficulty with this, I would encourage you to go to some other resources, Khan Academy, other textbooks. The internet's full of information, but it's important that you understand osmosis. And maybe I'm not describing it as best as I can, but this is the concept. And we have this equation, capital Pi equals mRT. So this is the osmotic pressure in atmospheres is capital Pi. It kind of looks like that. M is the molarity. R is our gas law constant, like we have in PV equals nRT. And obviously T is temperature. So we can also determine molar mass this way because we have molarity up in here. So we can use this the same way we just used Raoult's law and freezing point depression laws and things like that to determine molar weight and things like that. So it's pretty neat. And so I won't bore you with that because we just did one of those examples, but this is the basic concept. And there are processes like dialysis. There's processes like reverse osmosis, which is used in a protocol called desalination, which is not a protocol but a process, and so that's very important. When osmotic pressures are equal, we call that isotonic solutions. You may have heard of that in medicine, and this will be somewhat important, isotonic solutions. And even when you have things in medicine like edema, this tends to come from osmosis. So it's very important in medicine, fluid filling and things like that. We don't have to go into too much detail, but that's basically that. To finish this off, we're just going to briefly describe something called a colloid. A colloid. So a suspension of tiny particles in a solution is called a colloid. We don't have to get into this too much, but it's just important that you understand that there are solutions called colloids. And they scatter light differently. If you have a colloid and you've got little particles floating around, you can imagine that when you point light at it, it'll tend to scatter a little bit, and we call that the Tyndall effect. This is just sort of an introduction to these concepts. We might get into this in more detail someday down the road, we might not, but I think that we're going to end it there. So this was a quick chapter, chapter 11. I hope you enjoyed that, and we'll see you in chapter 12. Thanks a lot, everyone.